Hello, I'm going to do an example of solving a system of ODEs where the eigenvalues of the matrix A are complex. I'm actually going to be using my exact problem 3 from the webwork. Okay, so let's start. Let's start mentioning this is how it's said, dx dt. And as I mentioned in the previous video, this is really fair to use x that way, but I kind of prefer to put a vector symbol over this. So especially in this notation, we're saying that here the vector x, which is actually a function of t, so we can call it x of t, is x1 of t and x2 of t. And you can leave out that arrow, and it really is legitimate, and that's what webwork does. But again, I like to put it in there to remind us. Okay, so there's the 3 steps in the process that I talked about before. Step 1 is compute eigenvalues and eigenvectors of A. In this case, A is minus 1, 1, minus 2, 1. And a spoiler alert, they're complex and non-real. Okay, so in step 2, we need to find the general solution to the ODE. So remember, we have the ODE with an initial conditions, and the ODE has a general solution with, in this case, 2 constants. And the way that this works with complex eigenvalues is that we have x is, if I write this as e to the lambda 1 t v1 is still a solution, but it's complex valued solution, because the eigenvalue is complex, the eigenvector is complex, this is complex. So what we're going to do is write it as x sub r, the real part, plus I on the imaginary part, xi of t. So these are 2 real solutions. That's real valued vector. Here's a real. And so then the solution, the general solution then is going to be x is c1 xr of t plus c2 xi of t. That's going to be our plan. And then step 3 is going to be, okay, set x of 0 is equal to, in this case, -3, -1, and solve for C1, C2, it says period, and then substitute those back into the general solution. So it's a lot like what we just do for second order ODEs. Okay, we have these 3 steps. Okay, so let's go right on to go and do it. So step 1, compute the eigenvalues. So the characteristic equation is a determinant of A minus lambda I. I'm going to set that equal to 0. I'll use this notation. I noticed like Paul's note uses it, and you might have seen it. -1 minus lambda 1, -2 1 minus lambda. Those vertical bars means the determinant of that matrix. This is -1 minus lambda times 1 minus lambda minus 1 times -2. I'm going to set that equal to 0. So this is I get lambda squared, but the outer and the inner cancel. That's plus lambda minus lambda. And then the first term gives me a -1, and that's a +2 is 0. So it's basically lambda squared plus 1 is 0. So lambda is plus or minus I. Okay, so that's what we said here. We've got the eigenvalues. Lambda 1 is I. Lambda 2 is minus I. So that's the bad news, is it's complex. The good news is we only have to find one eigenvector. We don't have to find both eigenvectors. Okay, for lambda 1 is I, the eigenvector is A minus II times V1 is 0. And that becomes -1, 1, -1 minus I, 1, -2, 1 minus I, AB is 0, 0. So what are that? So that's the equations for the eigenvector V, which has components A, B. So we get -1 minus I times A plus B is 0, and we get -2A plus 1 minus I, B equals 0. All right, so even though these look different, they really are giving us the same information about A and B, and I can choose either one. I kind of like that one. It doesn't have any 2's in it. This says that B is 1 plus I times A. Bringing this term over to the other side with the negative sign. So I can choose A to be anything, and then B is given, well, almost anything. I can't choose A equal 0, right? But A equals 1 works, so then B is 1 plus I. So let's summarize. We have lambda 1 is I, and we have V1 is 1, 1 plus I. Okay. And I don't need to have lambda 2 because lambda 2 is minus I. V2 is 1 over 1 minus I, right? Okay, cool. So as I said before, we still get x is e to the lambda 1t v1 is a solution. And that in this case, it's e to the it times 1, 1 plus I is a solution, but it's complex values. So I'm going to write this using Euler's formula for the first part, cos t plus I sine of t times, we'll write this out too in terms of the real and imaginary part. I get 1, 1 plus I 0, 1. Right? Okay. So I'm going to, instead of foiling it, I'm going to floy it. F, L, O, I. The first term in this, that binomial times that first term is cos t times 1, 1. The last term is I sine t times I 0, 1. Then the outer is cos t times 0 times I 0, 1. Plus the inner term is I sine t. You need a little bit more room. We got cos t times 1, 1. That's first. Plus, Let's combine the i's. We get I squared. I times sine t times 0, 1, right? And then the outer, that times that, sorry, the outer, cos t times I times that. So let's bring the I in front. That's cos t times 0, 1. That's the outer term. The inner term is plus I sine t times 1, 1. Okay. And that sine of t, I kind of like to put the sine of t, but that works. All right. So notice that I squared is negative 1. So this is going to be cos t minus 0, 1. That's, sorry, cos t 1, 1 minus sine t times 0, 1. That's why I did FLOI. The first and the last both give you real functions. And then the outer and the inner both have an I in front of them. Okay. So actually, let's, I can combine, well, let's do it in 2 steps. There's cos t times 0, 1. And I'm factoring out the I. There's I times that, and I times that, plus sine t times 1, 1. So this is the x r of t. There's the real part of this is a real solution. And the imaginary part is also imaginary part that doesn't include the I. Right? Everything up to just this part. The thing that I multiplies is also a solution. So I'm ready to write down the general solution. We'll write it as x of t. You can sometimes just write x. It's going to be c1 times xr of t. And I'm going to combine this. First component is cos t plus 0. And then we've got second component cos t minus sine t. And then plus c2 times this part. On top, we've got sine of t. And on the bottom, we've got cos t plus sine of t. Okay, that's c1 times xr plus c2 times xr. General is x equals c1 plus c2, right? All right, now step 3, we're going to set x of 0, which is c1. Okay, I know the cos of 0 is 1, sine of 0 is 0, so this is 1, 1, plus c2, 0, 1. I'm going to set that equal to my initial data, minus 3, minus 1. Okay. So that's pretty easy system to solve. C1 plus 0 equals negative 3. C1 plus C2 is negative 1. So therefore, we get C1 is negative 3. And then negative 3 plus C2 is negative 1. Okay. So the solution to the initial value problem is x of t is going to be -3 times cos t plus sine t. Oops, that's a minus. I want to make sure we get it right. Plus c2 plus 2 times sine t. And then the second component is cos t plus sine t. And then we probably want to combine all these because they've asked me to fill in what the first component of the solution is and the second component. So -3 cos t plus 2 sine t is the first component. And then I'm going to have to combine things a bit here. I don't have to, but I want to. What's in front of cosine? -3 times cos t plus 2 times cos t. That's -1 times cos t altogether. Let's put that in cos of t. And then what's in front of sine t? Plus 3 sine t plus 3 sine t. That's a plus 5. All right, so we're now ready to fill in the answer. The answer is -3 cos t plus 2 sine t and minus cos t plus 5 sine t. All right, and I did this before. This is so prone to error that I made sure I did it before. I used my actual numbers just to make sure I got it right. And if I look at my work, yeah, I got it right. Now, I'm gonna stop now, but do another video with the geometry of this. They also ask about the trajectories. Are they spirals or what? So we can think about what the trajectories look at like and do some graphics on the computer with this in the next video. All right, goodbye.